Okay, let us summarize what we have said about information theory. So information theory deals with the problem of quantifying the amount of information which is exchanged by two entities. So for example, two people. So we looked at the example of Alice who is uncertain about a certain value of x, and then ask question to Bob, and you can quantify the amount of information that quantifies how much Alice is uncertain about x by the minimal expected number of binary questions that Alice has to ask to Bob in order to figure out what is the value of the random variable x. And so what we found is that entropy that say can be informally defined as the minimal number of binary questions, expected number of binary questions that Alice has to ask, can be shown to be equal to the entropy, which has this form here. Here I'm using log base 2. Okay. And this idea is formalized more clearly in the Shannon Theorem, where essentially we consider messages which are a sequence of n independent random variables, x. So we think of the problem of Alice and Bob, say, exchanging these messages many times, and every time the answer x to Alice's question is a random variable drawn from the same distribution independently. And then for this message, what Shannon Theorem tells us is that the minimal number of binary questions is equal to the entropy per character, per random variable, is equal to the entropy. Okay. And this has to do with the fact that we know that the property that messages of this type obey when n is very large are described by the asymptotic equipartition property that tells us that essentially with almost surely when n is very large, these messages will be in the set of typical messages. Okay, and so the idea of Shannon Theorem is that essentially you only need to code typical messages, and then the number of bits that you need to code or the number of binary questions that you need to ask is only the one to elicit typical messages, okay, that correspond to typical messages. Okay, so this, by the way, implies that I can define also the joint entropy, so that the entropy of a sequence of random variables, so the notion of the entropy can be generalized to a sequence of random variables, And this, the definition of this is just that this is minus the expected value of the log base 2 of the probability of the message of this string of random variables. Okay, so this is the general definition of the joint entropy. Now, if xi are IID, then we know that the probability of x1, xn is the product over I from 1 to n of the probability of the xi. And so this means that the entropy of the sequence is, if I put this here, then the product inside the logarithm becomes the sum of the logarithms, and then this is essentially minus the entropy minus the sum over I of the expected value of the log raised to xi of the probability of xi, sorry, which is essentially the sum of the individual entities. And if they are also identically distributed, all these are equal, then this is just n times the entropy of a single random variable, let's say x1. Okay? So indeed, this is the property that we have used in Shannon Theorem to show that actually the number of binary questions, the minimal number of binary questions that you need to ask per single answer is equal to the entropy. Okay, you can also generalize this notion of joint entropy to conditional probability distribution and define the conditional entropy. So imagine now that you have two random variables, x and y, and they have a certain distribution Pxy, which is equal, which I can write also as P of x given y times P of y. Okay, then imagine the situation where Alice so Alice wants to know about x, but she doesn't want to ask directly about x because maybe it is embarrassing. So imagine that Alice wants to know from Bob whether Carl is engaged or not, but instead of asking about x directly, she may ask about a different random variable, y. Okay, so maybe whether Carl went to the party with someone, or whether he was alone. And okay, so now because x and y depend on each other, when Alice knows about y, then her state of uncertainty changes from this one to the state of uncertainty on x, given that y is known. Okay, this is measured by the conditional entropy, which is just the entropy of the conditional probability distribution. Okay, so In this notation, I remind you that x and y are random variables, so the expected value is on the probability distribution of the expected of these random variables. So when I write this, what I mean is minus sum of x and y, p of x and y, log base 2 of p of x given y. Okay, so so this is the conditional entropy, which is essentially what is the quantify how the uncertainty of Alice about x if she expects to know y. So notice that y, we take an expected value also y. So this is again a quantity that we estimate a priori before knowing x and before knowing y. Okay. Okay. So notice also that if x and y are independent, then the conditional entropy of x given y, I mean the probability if they are independent, then this probability distribution is just p of x, doesn't depend on y. So the entropy is just equal to the entropy of x. So this quantifies precisely that if two random variables are independent, then by knowing a random variable y, you don't learn anything about x. Okay? And accordingly, if two random variables are, if you have two random variables in general, then you can vary their joint entropy. Because of this, you can write the joint entropy as the entropy of x plus the entropy of y plus the entropy of x given y. Okay? Because you just substitute these in the definition of the joint entropy. Okay? And what this tells us is that if the two random variables are independent, then this, as we said before, is just the sum. Okay? If x and y are independent. Okay? Okay, so now there is another quantity that I want to introduce now, which is which will be very play an important role in what follows. And this is the differential entropy. Okay, so sorry, okay. The relative entropy. This is also called the Callback Leibler divergence. Okay, so what is the problem that we want to discuss now? So imagine that this same setup here of Alice and Bob. Now as we said, so the minimum number of binary questions is given by the entropy, but this provides that Alice now knows the probability of X. Okay. Now imagine that Alice makes an error in estimating the probability of X, or that Alice believes that X is actually drawn from a different distribution, Q of X. Okay? Then the number of binary questions that she would do is essentially equal to minus the expected value of the log base 2 of Q of X, which is minus the sum over X of log of P of X log Q of X. And so this will be different from the entropy. And if we want to understand what is the difference, then we can write this as H of X. Then we can add and subtract here the expected value of log Q of P of X. And you see that when you take the minus sign, you have the entropy. When you take the plus sign, you can put these two terms together, and in a term which is the expected value of the log base 2 of P of X divided by Q of X. And I remind you that this expected value is taken over the probability P. Okay, so this term here is called the Callback-Leibler divergence. So we define the Callback-Leibler divergence, we write it in this way, as the expected value over P of log base 2 of P of X divided by Q of X, which is sum over X in its domain of P of X log base 2 of P of X divided by Q of X. Okay, so and this is essentially, this measures the extra or the inefficiency or the how much the error in estimating P of X costs to Alice in terms of expected questions, expected number of questions that he has to ask to Bob, okay, or the additional length of the code that B has to use to send messages to X in the perspective of coding. Okay, so the first thing is to show is this really a cost? I mean, the fact that the entropy is the optimal number of the expected, is the optimal way to ask questions, suggests that this must be positive, so that the Callback-Leibler divergence must be positive. And indeed, this is true because we can rewrite this as minus the sum over X in key of P of X log of Q of X divided by P of X. Here I just changed the sign and inverted the the argument of the log. And next we can use the fact that log of x is less or equal than x minus 1 for all x, for all positive x. And so this means that if this is less than 1, then with the minus sign this is larger or equal than the minus the sum over x in key of p of x. And when I substitute this with this, I get q of x divided by p of x minus 1. Now you see that in this term, this cancels with this, you have the sum over x of q of x, this gives you 1, and in this term you just have the sum over x of p of x, which gives you 1 because of normalization. So this is exactly equal to 0, which means that the Callback divergence is always positive. Okay? So notice one thing that you can also generalize this notion of the Callback divergence for continuous variables. And for continuous variables, then you define a Callback divergence between two distributions as the integral in dx of e of x log base 2 of p of x divided by q of x. Now notice that as we said, for continuous variables, the entropy, when you define the entropy is not invariant if you make a change of variables y, which is equal to f of x, where this is a monotonous increasing function. But instead, the Callback divergence is invariant, so this is equal to the expression for the transform variables, because p and q transform in the same way. Okay, because say dx of p of x is equal to dy of p of y, but also dx q of x is equal to dy q of y. So essentially, because the ratio between q of x, p of x and q of x is equal to the ratio between p of y and q of y, when y is computed as on f of x. And so the Callback divergence is invariant under this reparametrization or changes of variable. So indeed, the Callback divergence, you should think of the Callback divergence as a notion of distance between distributions, and it's a notion of distance of distribution which is invariant with respect to the variables with which on which the distributions are expressed. And so indeed this, so it's not exactly, it's called divergence because it is not a distance. So it does not, for example, the Callback of QP is different, is not symmetric. So it's not a distance, a proper distance in general. and also it does not satisfy the triangle inequality. So strictly speaking, it's not a distance, but still it measures how far is one distribution with respect to the other one. Okay. So in this case, for example, the Kullback-Leibler divergence measures how far is Alice's beliefs on X far from the true, where Q of X correspond to the belief of X, and P of X correspond to the true distribution. Okay. Okay, so there is another concept or quantity that will be very useful, which is the mutual information. So mutual information is, let us take again this example here, where Alice is wondering about the value of X, and her uncertainty about the value of X is quantified by the entropy. And then she asks Bob about Y, and what she can measure is so her state of uncertainty when she will know Y is expected to go from this entropy to this entropy. Okay, so. And then what is important to ask is what is the change in how much the uncertainty of Alice is reduced. And this is given by the difference between her initial uncertainty and the final uncertainty. Okay, so this is called the mutual information. You can think also at this situation as a situation where you have a certain theory, X, you are a physicist, you have a certain theory X, and of course you cannot ask God whether your theory is right or not, or what is the right theory, but what you can do is to make an experiment, and the experiment will return you some data, and the data will reduce your state of uncertainty about which theory is correct, hopefully, and so the mutual information tells you how much, in this particular situation, tells you how much you learn about your theories when you do an experiment, okay? And essentially what you can do is to measure, so to, in this case, try to design experiments that will give you as much information as possible on your theories. Now the interesting thing is that if you write this down, this is minus the expected value of log base 2 of P of X. So you can write this as the expected value of P of X given Y divided by probability of X, which means that you can also write this as the expected value of log base 2 of P of x and y, rather P of x times P of y. So this is exactly equal to the Callback divergence between a distribution, the joint distribution of x, and the marginal distributions of y, where essentially your P of x is just the sum over y of P of x and y, right? And so this tells you two things. So first of all, that the mutual information, actually it tells you three things. First of all, that the mutual information is a Callback divergence, so this is always positive. So you always expect to learn something when you do an experiment, or you always expect to learn something when you pose a question. Second thing, it tells you that this measures the distance between the joint distribution and the distribution of the two variables if you neglect their dependence. Okay, if you don't assume, if you neglect that x and y are independent, then this would be your assumption of the probability, and the Callback divergence tells you how far this belief is from the truth. Okay. So, in other words, the mutual information, it's a universal or say fundamental measure of the statistical dependence between variables, because the Callback divergence between two distributions is equal to 0 only if the two distributions are exactly the same. So the mutual information is a much more sensible measure of statistical dependence of correlation or covariance, for example, because it is equal to 0 only when two random variables are exactly independent. Okay. So the third thing that you learn from this is that the mutual information is actually symmetric between x and y. So indeed, you can write this also as the entropy of y minus the entropy of x minus the entropy of y given x. Okay? And so, if I go back to my example, this tells you that how much your experiment is going to tell you about the theory is exactly equal to how much your theory can tell you about the outcome of the experiment. Okay? So, as a final remark, notice that this also, so you can also write this as the entropy of x plus the entropy of y minus the joint entropy of x and y and the fact that this is positive tells you that the maximal value that the joint entropy between two variables can take is the sum of the entropies of the two variables, of the marginal distribution of the two variables. okay, which we already saw. So, in some sense, this quantifies the idea that if you are maximally uncertain about a certain number of random variables, then you should assume that they are independent. Okay, because this is what corresponds to a state of maximal uncertainty or to a state of maximal entropy. Okay, so the other interesting consequence of the fact that you can write the mutual information of two random variables as a Callback-Clymer divergence implies that this is invariant if you make changes of variables. So if you say that x goes to another random variable z, which is a function of x, and if you make a change of variable where y goes to another random variable, say w, which is another function of y, and if f is an increasing function and g is also an increasing function, then essentially the mutual information between x and y will be equal to the mutual information between z and w. Okay, because when you have a one-to-one mapping between variables, then you are not losing any information. Okay. Okay, very good. So now the last comment that I want to make is that the mutual information is the amount of information that you expect to learn on X when you know Y, but it's not actually the actual amount of information that you will learn. Okay, so in a sense that this is a quantity that we estimate before we do the experiment, before we know Y, but after you know Y, your state of uncertainty, you can be less uncertain about X, but also more uncertain about X. Okay, so let us make a simple example, and let us take two random variables, say X, that can take two values, 1 and 2, and Y that can take two values, say 1 and 2. And let's imagine that the probability that X and Y both take value 1 is equal to 0. The probability that X takes value 2 and Y takes value 1 is 3 over 4. The probability that X takes value 1 and Y 2 is 1 over 8, and this is 1 over 8. Okay, so these are two random variables. So the marginal distribution, you can compute the marginal distribution of X by summing over Y. This will be 1, 8, and 7 over 8. Okay, so this is the distribution of X. And the distribution of Y will be 3/4 and 1/4. Okay, with these numbers now you can compute, well, what is your initial uncertainty about X, is the entropy of X. So this is the log of 1/2 is minus 1/8 log of 1/8 plus 7/8 log of 1/8. So this is essentially the log of 1/8, which is 3, minus the log minus 7/8 of log of 7. Okay, so this is, if you compute it, is 0.544. Okay, so this is your initial uncertainty. So what is h of x given y? So now your p of x given y is given by if so the distribution of distribution of x is if y is equal to 1 is just a delta function, a delta on x equal to 2, because if y is equal to 1, x can only be equal to 2 with probability 1. Okay, so this is essentially 3/4 times 0, because the entropy of this distribution is 0, plus with probability 1/4, which is the probability that y is equal to 2, you have a distribution which is 1/2, 1/2. Okay, because if you normalize it here, so this is corresponds to an entropy of 1 bit. Okay, then indeed you see that you expect that your uncertainty about x will decrease from 0.544 to 1/4. Okay. However, if actually it turns out that y is equal to 2, your uncertainty will increase. Your uncertainty on x, if y is equal to 2, in this example, is equal to 1, and this is larger than this. Okay, so your uncertainty in this experiment can decrease to 0 or it can increase to 1, but on average it will decrease. Okay. Okay.